Okay, so as you can see here, we have some questions from the properties of solids. So these questions, they are based on the three modulus of elasticity. We need to see where to use the which modulus of elasticity. So once we are aware that which modulus of elasticity will work for the given situation, we can use the formula. Okay. There is one more concept, that is Poisson's ratio. We'll deal with it later, but let's start with questions first. So first question here, a 100-meter long wire having cross-sectional area of 6.25 multiplied 10 to the power minus 4 meters square, and Young's modulus is 10 to the power 10 Newton per meter square, is subjected to a load of 250 Newton, then the elongation in the wire will be. So which formula will be using here? Kavian and Sriyuta, which formula we will use here? Sriyuta, we will be using the formula for Young's modulus, right? As Young's modulus is given by the normal stress over longitudinal strain. So the longitudinal strain is given by change in length over original length. See, we obtain it like this, that stress over strain hundred meter long wire. So original length is given. Original length we write as 100 meter, and we its cross-sectional area A is given as 6.25 multiplied 10 to the power minus 4. Young's modulus is given as 10 to the power 10 Newton per meter square. We are given the load, so that force is given as 250 Newton. Now we'll find out the stress and the strain. So stress is equal to force per unit area. Stress will be equal to 250 divided by 6.25 multiplied 10 to the power minus 4. So you will be getting this 250 over can take 625 multiply 10 to the power 6. Then it would be 10 over 25. So stress we are getting here 10 over 25 multiply 10 to the power 6. You can write it as 100 over 25, that is 4 multiplied 10 to the power 5 Newton per meter square. So this is the stress, and now we need to find out the strain. So using the Young's modulus, we know that stress over strain will be equal to the Young's modulus. So strain will be stress over Young's modulus. Stress divided by Young's modulus will give you the strain, and stress is 4 multiplied 10 to the power 5 divided by Young's modulus, which is 10 to the power 10. So we get the value of strain as 4 multiplied 10 to the power 5 is equal to strain minus 5. This is the strain. Then using the definition of strain, as we know that strain is delta L by L, change in dimension by original dimension. So we write here delta L will be equal to L multiply 4 multiply 10 to the power minus 5. So L is given as 100. If you multiply this 100 by this, you will get 4 multiply 10 to the power minus 3, which is 4 millimeter. So change in length of the extension produced is 4 millimeter, or 4 multiplied 10 to the power minus 3. So which option is correct here?
Option 4.
Option 4. Okay. So will you try to do one question on yourself?
Yes, sir.
You just need to apply the formula of the modulus. Okay. So see, our next question is this is, you have assertion A. Okay, assertion. A steel is used in the construction of buildings and bridges. and a region is steel is more elastic and its elastic limit is high. In the light of above statements, choose the most appropriate answer from the given system. So what can you say about the assertion? Is assertion correct or incorrect?
It's correct.
It's correct. As steel can withstand a higher load, so we will get here that steel will have a higher elastic limit and it's more elastic. So steel is more elastic, that's true. And region steel is more elastic. Okay, steel is used in construction, that's correct. And steel is more elastic and its elastic limit is high. This is also true. So both are correct and region is the also the correct explanation. Both A and R are true, are correct. But okay. So correct option will be option 3. Both A and R are correct. And R is the correct explanation of it. It's correctly giving that why we are using steel in the construction industry, construction of building and bridges, why we are using steel. Okay, you have been given a graph here. See, as shown in the figure, in an experiment to determine the Young's modulus of a wire, the extension and load curve is plotted. The curve is a straight line passing through the origin and makes an angle 45 degrees with the load axis. The length of wire is 62.8 centimeter and its diameter is 4 mm. The Young's modulus is found to be x multiplied 10 to the power minus 4 Newton per meter square. The value of x is. So you have to find here the value of x. So eventually you need to find out here the Young's modulus. So to find the Young's modulus, you need to find out stress over strain. Okay. So stress divided by strain will give you the Young's modulus. So you are given everything here. The angle is also given. So how we will find out? Putting the values here, stress is F by A. Stress is F by A and divided by strain. So strain is delta L by L. This is your Young's modulus. So you will get F by A multiply L over delta L. So this you will get as the Young's modulus. So area and length, they are given to you. See, the length of the wire is given as 62.8 centimeter. And area you can find out since the diameter is given. The diameter is given as 4 multiply, given as 4 mm. Okay. So you just need to find out everything. Now, if you observe from this graph, you can observe there is a 45-degree angle between extension and load. So if you find out this, from this graph, if you try to find out F over L, that means load over extension. If I find out load divided by the extension, extension is represented by delta L. So what value we will can I get from this graph? If I am getting F by delta L, so what is the expected value? Yes, from the graph, as we can see, the angle between force and extension is 45 degree.
Sir, will it be 1?
Yeah, it will be 1. So from our values, we can get here F by delta L. This we know as 1. And here we just need to find out L by A. This should be equal to the Young's modulus. Okay. So F by delta L is 1. You can remove this. So 1. And L by A should be equal to the Young's modulus. Okay. Now, to find out, L is given as 62.8 centimeter and diameter is given as 4 mm. So we will be using here the SI system of units. We will convert the 62.8 centimeter to meter. So you will get L as 0.628. We get here 0.628 meter divided by the area. The area is given as pi r squared. So it's pi r is 2 multiply 10 to the power minus 3. So you get this one whole square. Now, this is our Young's modulus. So if you simplify, you get 0.628 over pi. And here multiply 2. In the numerator, you will get here 10 to the power 6. As you can see, the value of pi is 3.14. And if you multiply 3.14 by 2, you will be getting 6.2. See, 3.14 multiply 2, that you get 6.28. So that's what in the numerator. So by putting the value, you will be able to cancel all these terms. So let's write it as 6.28 and denominator also as 6.28. So you will have here you will get in the numerator, you are getting 6.28 over 6.28 and multiply 10 to the power, you are getting 5. So this value again comes out to be 1. So comparing it with the Young's modulus, which is given x multiply 10 to the power 4. So what should be the value of x here? We have 10 to the power 5, where it's given here 10 to the power 4. So the value of x can be obtained by writing it as 10 multiplied 10 to the power 4. So what should be the value of x?
10.
10. Okay. See, everything is hidden. If you are given about the Young's modulus, apply the formula of the Young's modulus, use the data given to you. Okay, from the graph, whatever we can obtain. So use that and you'll get your answer. So now move to the next one. The value of x is 10. Choose the correct relationship between Poisson ratio, bulk modulus, and the modulus of rigidity, eta, of a given solid object. So I think we have not discussed about the Poisson's ratio. So once we discuss about the Poisson's ratio, we'll include all the three. Okay, we'll see how all three are included with each other, how all three can be included in one. Let's see here. A force is applied. I'm giving you 5 minutes. Try to do this. If let me see how much you can attempt. A force is applied to a steel wire A, rigidly clamped at one end. As a result, elongation in the wire is 0.2 mm. If same force is applied to another steel wire B of double the length and a diameter 2.4, that of the wire A, the elongation in the wire B will be, that we have to find out. Okay. So what concept is to be utilized here? What do we think what we can utilize here? You are given two steel wires. Okay. They are different in their length and area of cross section. So you have here one steel wire and you have another steel wire. So these two wires, they are different in their area and they are different in their length. So what value should be same for both of them? What relation do these two wires owe with each other? See, the wire A is also made up of steel. This is also made up of steel. And this wire is also made up of steel. Okay. So we have a connection between them. The connection is that the Young's modulus of both the material will be the same. Young's modulus does not depend. It's a constant for a given material. For a material, not for a given dimensions. Whatever dimensions be there, the Young's modulus of that material will remain the same. Okay. So you can use here the Young's modulus of both the material will be the same. So a force is applied to steel wire A. This is your steel wire A, rigidly clamped at one end. As a result, elongation in the wire is 0.2 mm. So suppose it has the original length L and the extension that is produced here, delta L is 0.2 mm. when you have some load attached to it. So you have some load attached to it, you have some extension. So the force F. Now, if the same force is applied to another steel wire, so this is another steel wire, and here also we apply the same force F. The force applied is the same F, but the steel wire B, it has the double length, so its length is 2L, and its diameter is 2.4 times that of the wire A. So suppose if this wire has the radius R, so this will have its radius. The radius of this new wire will be equal to 2.4 R. This will be 2.4 times of R. Okay. So this condition is we have known. Now, if we have a relationship between the radius, so we can find out the relationship between the area also. Since let area A1 be the area of this first wire and area A2 be the area of the second wire. So we can find out the ratio as pi R1 squared over pi R2 squared. So pi and pi cancel, and you will simply get here R1 is simply R and R2 is 2.4 R. So you will get here R squared over 2.4 squared R squared. So the ratio of the areas will be 1 over 2.4 squared. And 2.4 squared is 576. Is it 576? So you get 5.76. This is the ratio of the areas. Now we can simply use the values of the Young's modulus, find the Young's modulus for wire A, Young's modulus for the wire B, equate both of them since the Young's modulus will be same for both the wires. Okay. So can you do it now?
Yes, sir.
Try doing it. We have to find out delta L for the second wire. For the second wire, we have to put here delta L. That's what we have to find out. The Young's modulus given by stress by strain. So it is, we just solve F by A, and the strain is delta L by L. So you will get here delta L, and here you will have L. Okay. So this is your Young's modulus for the first one. Should be equal for the second one also. So for the second one, your force is same. Length is 2L. Area of cross section. This is your A1. This is the second area of cross section A2. And delta L that we have to find out. Let us make it as delta L dash, since the change in dimension would be different. So clearly F and F cancel, L and L cancel. So you can put here A2 by A1 multiply delta L should be equal to 1 by delta L dash. But we want delta L dash. So our delta L dash, that is the new change of dimension, should be equal to area multiply delta L over second area A2. So A1 over A2 we have found out. A1 over A2 is 1 over 5.6. Okay. You have just have to multiply it by delta L, which is 0.2. So solve it out. A1 by A2 is 1 over 5.76. This is 1 over 5.76 multiplied by delta L. Okay. So delta L is given as 0.2 mm. You put here 0.2 and then you will get your answer. Okay. So what should be the expected answer here?
Sir, is it option 4?
Yeah, it is option 4. 3 times 10 to the power minus 2 mm. See here, all are based on the modulus of elasticity. A thin rod having a length of 1 meter and area of cross section 3 multiplied 10 to the power minus 6. So you have a thin rod. A thin rod having length 1 meter, area of cross section is given, is suspended vertically from one end. The rod is cooled from 210 degrees centigrade to 160 degrees centigrade. After cooling, a mass is attached at the lower end of the rod such that the length of the rod again becomes 1 meter. Young's modulus and coefficient of linear expansion of the rod, they are given respectively. The value of m is, we have to find out the mass that is attached at the lower end. So eventually you have to find out here force that is there. So this question, it utilizes your two concepts. It utilizes the concept from uh, thermal expansion. So if you remember, if you recall the formula of thermal expansion, so you have the new length L dash is equal to L times of 1 plus alpha multiplied delta T. So you have L dash by L is equal to 1 plus alpha times of delta T. What is this value L dash by L? Can we call this to be the strain?
Yes, sir.
Yes. So this is the same as the strain that has been produced. So L dash by L is equal to 1 plus alpha times of delta T. Here they have given the value of delta T. We know the value of alpha. Okay. So we can put here this value and get the value of L dash by L. The original length we have obtained as L. Original length is given to us as 1 meter. So L dash we can find out. We can find out L dash will be equal to 1 multiply 1 plus alpha. So alpha is 2 into 10 to the power minus 5. This is 2 into 10 to the power minus 5 and multiply delta T. So delta T is to be taken as final minus initial. So it's 160 minus 210. That is minus 50. So L dash or new length will be equal to 1 minus 100 multiply 10 to the power minus 5. So this is length we have 1. This is 1 meter minus 10 to the power minus 3 meter. You can convert this to millimeter and hence obtain the value of L dash. So L dash will be equal to, if you find out this, it will be equal to 999 meter mm. As 1 meter is equal to 1000 mm. So 1000 minus 1, 10 to the power minus 3 is mm. So you get 999 mm was the new length. Now after hanging the mass m, if you hang the mass m, so from this length, now this becomes the original length. So this becomes the original length. From this original length, it again gains its new length. So now the extension produced is 1 mm. Okay. So using the value Young's modulus. Shall I stop? Can you do this now? The
Yes,
puzzle
sir.
is solved almost. Okay. Try to do this. Now this is your original length and your new length is 1 meter. So you get your Young's modulus F by A multiply delta L multiply L. Okay. So now Young's modulus is given as 2 multiply 10 to the power 11 equal F we do not know, that is what we have to find out. Area. Is area given here?
Yes, sir. It's 3 into 10 to the power minus
Yeah,
6.
area is given here. We put 3 into 10 to the power minus 4. Minus 6, sorry. 3 into 10 to the power minus 6. And multiply L. The original length is 0.999. So you can use it in mm also. Since it's L by delta L. So here you get 999. That is in mm. And the new change in length is just 1 mm. So 999 by 1. That's the answer. Now, transpose the terms. You get here 6 multiply 10 to the power 5 over 999. This should be equal to the force. And force can be written as MA, mg. So we just need to find out the value of g here, m. So mg divided by g. So taking g as 10, you get 6 by 999. And here you have 10, multiply 10 to the power 5. This is the mass. Now, see this 999, if you can approximate this 999 to be 1000, if you take this to be 1000, so you get here 6 multiply 10 to the power 1. That's the mass. And hence 60 kilogram. 60 kilogram is the mass. See, why I have approximated it, even if you divide it by 999, you will be getting your answer as a 5.999 something you will be getting. Okay. So 59.99 something you will get. So that is approximately 60 kilograms. So the value of M is approximately 60 kilograms. So see, the question involved two concepts. It involved the thermal expansion as well as the Young's modulus. You should be able to remember the formulas. Like the change in length is given as L dash equals to L multiply 1 plus alpha times delta T. In similar way, superficial expansion is also given. Then you have volumetric expansion. Okay. So here is the new question. Okay. So here you have to find out the velocity of longitudinal wave in the rod. Okay. So try doing this. I'm just coming in 1 minute. Try to do this. Do you know the formula of the velocity of wave?
No, sir.
So just check it out. Use the formula of velocity of wave. The velocity of wave, it depends on the properties of the material. It depends on the Young's modulus of the material. So how it depends? Just go about it once. You have studied the longitudinal waves in a solid. Okay, thank you for waiting. I'm back again. Okay, so did you get the formula for longitudinal wave?
Yes, sir.
Okay, so what is the formula?
V over root over y by density.
Yes, root y by density. So you can use and you can obtain the answer now. So did you get the answer?
Yes, sir. Is it option 4?
Okay, let's see. So here you have the formula. V is equal to under root of y by rho. So this is under root of 5. Young's modulus is given 3.2 multiplied 10 to the power 11 divided by density, which is 8 multiplied 10 to the power. So if you divide, you get here under root of 0.4 multiplied 10 to the power 8. So you can write it as 40 multiply under root 10 to the power 6. So 10 to the power 6, the taken root is 3, 10 to the power 3, and square root of 40 will be greater than 6. It will be greater than 6, so that your option 4. Are you getting the fourth option?
Yes, sir.
So this is how we find out the velocity of longitudinal wave. So in the similar way, you also have the velocity of a transverse wave. See, the velocity of a wave through a medium, it depends on the properties of the medium. So see, use of properties of solid in wave. Now, under the same load, a wire A having length 5 meter and cross-sectional area 2.5 multiply 10 to the power minus 5 meters square stretches uniformly by the same amount as another wire B of length given and area of cross-section. The ratio of Young's modulus of wire A to that of the wire B. So try to do this. I'm not solving it out. I'm waiting for 2-3 minutes. The load is same. So force is same for both of them. So you can find out the first Young's modulus y1 F by A1 L by L. Then you have y2 F by A2. Here again you have delta L multiply L. So F is same for both of them. Delta L is also same. So you can cancel out delta L also. And you get the value y1 by y2 equal to A2 by A1. And here you have the length of first L1 divided by the length of second L2. So all the values are given. What should be the answer?
Sir, is it option 2?
Okay. So you say it's option 2. Let's check it out. A2 is 3 multiplied 10 to the power minus 5 and divided by A1, which is 2.5 multiplied 10 to the power minus 5 multiplied by L1. So L1 5 meter and L2 6 meter. So it's 5 by 6. Now 10 to the 5 and this one cancel. And so the answer is same. It's 15 by 15, which is 1. So 1:1 is the answer. Answer is 2. So I think we have completed this chapter. In this chapter, I don't think that you people have any doubts.
No, sir.
Almost all the doubts are clear. One thing just you need to go about the Poisson's ratio that we have not discussed. We left out one question. So try doing that one question from the Poisson's ratio. So just let me send this in the group and try doing this. Once you have done this one, we'll be starting with the new chapter. We have done SHM. We have done properties of solid. So from tomorrow, we can start with properties of fluids.
Okay,
So
sir.
from, okay, bye.
Thank you, sir.
Bye. Thank you.